Hi everyone. So today we are going to talk about more about tests and interval. The central limit theorem for the mean of the sample, sampling distribution, and also the degrees of freedom. And we learned about how to calculate the confidence interval for means. We learned about t-value, t-statistics, and hypothesis test and confidence interval. What's the similarity and differences. Okay, and we talked about hypothesis tests start with the parameter and ask if the data are consistent with the value, while the confidence interval starts with the data and find the interval of plausible values for where the parameter may lie. I'm going to tell you what is the meaning of p-value in more depth today. So as I said, the p-value is the probability of observing data given the null hypothesis is true. And it's really not the probability of null hypothesis being true given the current data. But intuitively, we may think the p-value, the meaning of p-value is like this. But it's not true. So basically, p-value is the conditional probability of getting the data given the null hypothesis is true, and not the probability that the null hypothesis is true, and not the conditional probability that the null hypothesis is true given the data. And let's say we got the p point of 3, and what does that mean? That does not mean that there is a 3% chance that the null hypothesis is true, and does mean given the null hypothesis, there is a 3% chance of observing the observed statistic value. Very important. And let's say you got the small p-value, and first of all, it's a good thing, yay. But as we talked about, it means the results we just observed is unlikely to occur if the null hypothesis is true, and does not mean that the null hypothesis is less true. And how small the p-value should be, it really depends on a lot of things. For example, your prior belief in the null hypothesis and your trust in your data, in the experimental method and the survey protocol. P-value serves as a measure of the strength of the evidence against the null hypothesis. It should never serve as a hard and fast rule for decision. So it's really the degree of the strength, okay? And when you make the decision as a scientist, as a researcher, you have to take the responsibility for the decision on yourself. Therefore, we need to be careful about making decisions using the p-value. And we really need to know what the p-value means. And what happens when we get the high p-value? That means there is no evidence for rejecting null hypothesis, and we cannot reject the null hypothesis. For one-sided test, if p-value is higher than 0.05, that means you know that your test statistic is the wrong side. Because it's only testing one side, the red area is larger than 0.05, you are on the wrong side. And high p-values mean what we've observed is not surprising at all, given the null hypothesis is true. And we have no reason to reject our null hypothesis. So therefore, we are saying we failed to reject the null hypothesis. But it does not prove that the null hypothesis is true, and do not say that you accept the null hypothesis. You cannot say. And you should say the data have failed to provide sufficient evidence to reject the null hypothesis. Therefore, we can say fail to reject the null hypothesis. So these kinds of p-values and null hypothesis testing, we need this to make decisions. On Alphalevel defines how small the p-value should be. As I said, it really depends on a lot of things. The Alphalevel means the threshold for a decision, and significance level. So you can find this phrase in papers like statistically significant. And we are writing that using this alpha Greek letter, and common Alphalevel include 0.05, 0.01, and 0.01. And there are important considerations. The thresholds Alphalevels are arbitrary, as I said. It's really arbitrary. But we need something for decision making. You must select the Alphalevel before you look at the data. If you choose the Alphalevel after you look at the data, your results are likely to be biased. In some fields, the decisions about the significance is presented with stars. Like 1 star, p less than 0.05, 2 stars, p less than 0.01, 3 stars, p less than 0.001. But still, it's better to report the p-value in addition to the stars. We can make wrong decisions, right? Because the alpha level is arbitrary, and many times we can make wrong decisions, but there are two types of errors, wrong decisions. So one is type 1 error, that is when the null hypothesis is true, we mistakenly reject it. That's false positive. And type 2 error is the null hypothesis is false, but we fail to reject it. Okay, so that's false negative. So we say, oh, there is no results, no significant results, but in truth, there is. So we can say, so this is the truth, null hypothesis is true, and null hypothesis is false, and this is my decision from my data, and reject the null hypothesis, and fail to reject the null hypothesis. These are the correct answers, but these are the errors. So this is type 1 error, and this is type 2 error. So the probability of type 1 error, we write that as a alpha. This is the same with the alpha level we just learned. And to reject the null hypothesis, the p-value must fall below alpha level. It's basically, we are controlling for the type 1 error, the probability of the type 1 error to alpha. And a type 1 error, it can happen only when null hypothesis is true. And the probability type 2 error, we write beta. As we said, the type 2 error is null hypothesis false, but we fail to reject it. And beta is the probability of this type of mistake. And beta is harder to assess than alpha because we don't know the true value of parameter. And there's a trade-off between type 1 and type 2 errors. This graphical view really explains that. Let's say this is a sampling distribution when we assume the null hypothesis is true. And let's say this is for alternative hypothesis. And if the null hypothesis is true, this area, if we observe some data on this area, we are going to reject the null hypothesis, but null hypothesis is true. So this is the type 1 error, the probability of type 1 error. We call it alpha. And let's say the alternative hypothesis is actually true. And then if we observe the data here, in this area, we cannot reject the null hypothesis, right? We fail to reject the null hypothesis, but the null hypothesis is false, right? So this is type 2 error, and the probability of this area is going to be beta. And as you can see, we can decide a line, we can draw a line between these two distributions. And if we move this way, alpha is decreasing, but beta is increasing. We can get less type 1 errors, but more type 2 errors. And if we move this line into this way, the alpha could be increasing, but beta could be decreasing, right? So therefore, we are unlikely to get the type 2 error, but we are likely to get more type 1 error. So that's the trade-off between type 1 and type 2 error. The level of alpha is really important actually, because it'll influence the level of beta. But why most popular alpha is 0.05? It's actually from history. So Sir Ronald Fisher, he's one of the most famous modern statistician, and he suggests that 0.05 as a criteria for testing hypothesis, and he had in mind the small initial studies. So small studies have relatively little power. I will show you why. And Fisher was concerned that they might make too many type 2 errors with the low-powered studies. And that means we are going to fail to reject the null hypothesis, and once a test failed to reject the null hypothesis, so it is unlikely that researchers come back to that hypothesis and try again. Therefore, we miss the opportunity to examine the hypothesis. So that's another bad thing, right? He wanted to be generous about the type 1 error a little bit, but he didn't concern that much because that's what was in his mind was small but exploratory studies. And that should be followed by a replication or larger study, more confirmatory study. So for example, the probability of the type 1 error is alpha, in this case 0.05, and the probability of that two independent studies, so replication, would make the type 1 errors is 0.05 times 0.05 and 0.0025. So it's quite low. So Fisher was confident that type 1 errors in initial study were not a major concern. However, we are still using 0.05 highly powered studies with a large sample size. That means we might be too generous and we are going to make more type 1 errors. Another important concept is power, statistical power. So remember, we can never prove a null hypothesis true. You can only fail to reject it. When we fail to reject the null hypothesis, we can ask whether we looked hard enough, and we hope our study is strong enough to reject it. And the power of a study really is about that, the probability that it correctly rejects a false null hypothesis. With high-powered tests, we can be confident that we've looked hard enough even if our test failed to reject the null hypothesis. The type 2 error, beta, is the probability that a test fails to reject a false null hypothesis, and therefore the power is the 1 minus beta. That is the probability that it correctly rejects the null hypothesis. And whenever a study fails to reject its null hypothesis, the power of the test comes into question. If our power is really low, we cannot really believe that we failed to reject the null hypothesis, and maybe we might want to test it again with a larger sample size, for example, and with a higher power. But is power important only when a study fails to reject the null hypothesis? Actually, it's not. It's really important even when we can reject the null hypothesis. There's an important concept related to that, that is winner's curse. I'm going to show you a plot from this study, and there are two values. So one is the statistical power that we just talked about, the probability that we correctly reject the null hypothesis when the null hypothesis is false. Okay? And we can increase power with large sample size and large effect size. I'm going to explain this in a minute. And smaller, lower threshold. That means we are using really high alpha. As we said, there is a trade-off between type 1 error and type 2 error, and this means that we are increasing alpha, and then we are going to get the more power because we have the small beta and power is 1 minus beta. Therefore, if we increase the alpha, if we increase the probability of type 1 error, we are going to get more power. That means we are going to reject the null hypothesis more often, and then we can detect a real signal there. And here y-axis is the stronger results than real, the bias. And the relationship between these two is negative. That means if we have low power, it is likely that the results that are published can be biased, could be stronger than real. So low-powered study can increase biases in literature. Just at random, we can get the good results and then they publish it. That results in replication failure, and these papers are all about that. Why small sample size undermines the replicability, reliability of neuroscience, why most published research findings are false, low power increased the replication failure. And here, big correlations in little study, again. So inflated fMRI correlations, so this is a better results, stronger results reflect low statistical power. There's another important concept, effect size. So the effect size is the distance between the null hypothesis value and the truth, P and mu. And power is proportional to effect size. So large effects are easier to see actually and result in larger power. And small effects are naturally more difficult to detect, right? And the standard deviation is also important. It provides a ruler. And effect magnitude and standard deviation is basically signal to noise ratio, right? So there are different types of effect sizes. So for example, correlation based and distance based. And correlation based is R and R square. We learned about this. Cohen's d is defined by the differences between two means and divided that by the standard deviation. So it's similar to z-score, but Cohen's d is more about the comparisons between groups. And we already saw this. Power is here. We talked only about beta in the previous slide. In this picture, 1 minus beta, this is a power. As we said, there is a trade-off between alpha and beta, and the role of effect size in power is if p is farther than p0, like this, as you can see, 1 minus beta is increasing. So effect size is important. And also the standard deviation, the spread of this distribution is also important. And there's another important concept about the power and alpha, about alpha and beta. There's specificity and sensitivity. Let's say you have a test. This is a true condition, so condition negative and condition positive. Like for example, you don't have disease, so minus disease and plus disease condition. And then this is a test results, so positive results and negative results. And as we said, this is true positive and true negative. The specificity is about this column. So among the condition negative, what is the probability, what is the proportion of the true negative? So that is basically 1 minus alpha, because this is alpha. And sensitivity is about this column, and among the positive results, what is the probability of getting true positive? So that is 1 minus alpha, 1 minus beta, and that is same with the power. So how we can reduce both type 1 and type 2 error? We can make the distribution narrower, or we can move this distribution far from P0. So both methods are going to work. And how we can make this distribution narrower? That means we can increase the sample size, right? And we can increase the effect size. But if we have the fixed effect size, we can increase the sample size. And also, from this paper, because it's really hard to increase sample size sometimes, we can actually increase the power with the experimental design. And I'm not going to go really into this paper, but if you are interested in, you can find this. Okay, so that's it for today's lecture, and don't forget the quiz. Thanks, and see you in the class. Bye.